Hey, Gleb here, and welcome to yet another tutorial from the 2.80 plus update for hard surface modeling video course. Today we're gonna be talking about the weighted normal modifier. This tutorial will be split in two sections. In the first one, more theoretical one, we'll take a look at smooth shading and how per face vertex normals affect shading in Blender, and for that matter in other applications. We'll talk about the Blender default smooth shading algorithm and how face-weighted vertex normals can actually look better in terms of shading. And by better, I mean more faithful to the actual geometry. So flat faces look flat on rendering, and the interpolation occurs across the beveled edge and not across the entire model, like you see on the right. As we will see, the default Blender smooth shading algorithm is not ideal when dealing with large flat surfaces, and that's pretty much the essence of hard surface modeling. So the weighted normals are simply much better solution. And because lighting and shading calculations in any 3D software, including Blender, largely depend on vertex normals, it's crucial to understand how to manipulate these normals. And here comes the weighted normals modifier. Ta-da! So that's pretty much our agenda for today. I calculate better shading automatically using this newly introduced modifier. But here we have the reference object, which is a pretty high poly mesh, and right away I will switch to Workbench Render Engine and Matcaps. I'll pick a slightly glossy one, because with some reflectivity it will be easier just to spot all the gradients and talk about it. Yeah, that one looks pretty neat, but I'll stick to that one instead. And one more thing that I want to do is add the wireframe toggle to the quick favorites menu. Actually, I've already done it. So we can press Q and just quickly turn on and off the wireframe to take a look at the underlying geometry. Alright, so here is the reference mesh with almost perfect shading. Just due to the sheer amount of geometry thrown in. It's about 3,000 polygons or something like that. It's pretty impractical to have such heavy meshes in your scene, usually, but for the demo purposes, here we go. We'll use it as a kind of a reference to compare the low poly models with tweaked normals too. Alright, so let's get started. Fly, fly, fly. So thankfully there is more than one way of automatically calculating vertex normals in Blender, and let's take a look at some of them. So on the left there is a reference object, and on the right there are four meshes that share the same geometry, but that have different vertex normals. Here is the flat shading. Basically, that means that each face has its own set of normals. Here we can see the merged vertex normals, the averaged normals, so to speak, and two objects on the right display face-weighted normals, the factor of 50 and the factor of 100. And I wonder if you agree it resembles the reference object in a closer way than the average, the default algorithm. And that is simply due to the fact that the size of the face is actually taken into account in calculating the vertex normals. We will have a look at some concrete examples. But first, I will just go through how this scene was set up. This is just a few polygons with the solidify modifier added on top, and with the bevel modifier for decorative purposes, just to make it beautiful, I guess. So in order to see the normals in the edit mode, we can just go over to the overlays tab, and we have a bunch of settings that we can activate. For example, face normals, custom split normals, vertex normals, and so on. So let's see how it goes. First of all, I'm going to tab into the edit mode and then go over to the overlays tab. And at the bottom we have a bunch of icons. Face normals, vertex normals, and so on. Let's start with the face normals, because why not? Basically, face normal just points in the direction the surface is facing, the polygon is facing. You can see it here visualized with the light blue lines. An important thing to understand about face normals is that they don't affect shading. They don't directly participate in the shading calculations. That being said, face normals are used in calculating the vertex normals, like the direction of adjacent faces, which this vertex is a part of. But directly, face normals aren't used in shading calculations and thus aren't very interesting for us in this particular example. So let's switch it over to vertex per face normals or simply to vertex normals, which, by the way, don't take any part in shading calculations. Although they're called vertex normals, they're just a cross product between all faces that touch that vertex. That is not very interesting for us here when we talk about shading. Yeah, it may sound confusing because in different 3D modeling applications, these things are called slightly differently. In Blender, vertex normals aren't used for shading. What Blender uses for shading is actually custom split normals or vertex per face normals. Let's take a look at it. So I'll click to disable vertex normals and enable vertex per face normals, which we'll be calling just vertex normals from now on, just for simplicity's sake. Disclaimer: for the rest of the tutorial, when I will be saying vertex normals, what I actually will mean is split vertex normals or vertex per face normals. So, ta-da! You can see that each face now has its own kind of set of vertex normals. And these guys are actually the reason why when the light rays hit the surface, it looks like it looks, because render engines use this information for calculating the gradients across the surface of the mesh. And good news is that custom split normals, or yeah, let's call it vertex normals, can actually be manipulated. They can be disjointed like this to produce so-called flat shading, or just sharp angles between polygons, or they can be merged. And if two vertex normals point in the exact same direction, it produces a softer transition between the adjacent polygons. And ideally, on merging, it should look something like that. It will become clear in a moment why it has to look like that. But let's get back to our examples. In the case of the flat shading, you can see that the vertex normals are perpendicular to the face normal for each face practically, and it results in a sharp line, sharp transition between two polygons. What will happen if we right click and select shade smooth? Nothing yet, because we have to go in the objects data tab and make sure that auto smooth is enabled and crank up the angle of the auto smooth. So all edges fall into that range defined in the angle. 180 degree will definitely cover all cases. So we created shading that looks like our second example. So what happened to the per face vertex normals here is that they got merged, and not only merged but also averaged based on the face normal of the adjacent faces. And while it looks pretty smooth, it also doesn't look quite right based on the highlight that you can see. To make it slightly more clear, let's take a look at this example instead. Even though some surfaces are perfectly flat, the highlight is kind of skewed, and it will look skewed in every render engine you can imagine. In cycles, for example, we can also see that it behaves in a pretty weird way. Well, of course, it can be used for artistic purposes if you aim for that kind of look, but generally that is undesirable result. The smooth shading, or sometimes it's called the Gouraud shading, can look really bad on harsh angles. Like here is a good example, an averaged cube. There is no way we can tell that it's cube and the face of the cube are actually flat just by looking at the current shading. Something more than face normals should be taken into account, because not all faces are born equal. Like, look at this. Even though the faces presented here have different sizes, those in theory should have different weight, they contribute kind of equally to the end result. But ideally, this smaller face should have smaller impacts on defining the vertex normals. And on the contrary, this larger face should definitely make all the vertex normals belonging to this face point upwards to retain the flat look in the rendering process. I'm sure that by the end of the tutorial that will all make sense, especially when we will be trying different things with the weighted normals modifier. For now, we're just trying to lay the groundwork. Now let's take a look at slightly different example with even tighter bevels. You can see that the interpolation of lighting across this surface at the top looks pretty weird. It should be flat, right? It's a completely flat polygon. So why we see the gradient going on? To get the answer, let's return to our cube companion. And here is how it looks with the corner weighted normals or the averaged normals. So it's like a sphere somehow turned into a cube from the shading standpoint. Let's add the bevel now and see how it will look with a slight chamfer in between the faces. Introducing just a few polygons will make things look much better, because instead of averaging the vertex normal to 45 degrees in between the perpendicular surfaces, I will have a slightly different ratio that looks much better, or should I say much flatter, much closer to the flat surfaces at the top, bottom, at the sides of the cube. So here is how it looks without bevel. So yeah, these additional few polygons really saved the day, but we can do better than that, because even now, if we go ahead and take a look at the vertex normals, I mean the per face vertex normals of the top face, we'll see that they are not quite pointing up. They're not quite perpendicular to the face direction, and thus this face will never look flat. To demonstrate that, I'll use one of the new normal editing tools of Blender. I'll go Mesh, Normals, Set from Faces. What has changed is that now vertex normals are aligned with the face normal. To achieve a proper shading on the cube is basically to align all the vertex normals to the face normals of their respective faces. In other words, that would mean face weighting all vertex normals, so blending occurs only on the bevel face and not across the entire model. Alright, fine, after some theory on normals in Blender and how they affect shading, let's actually move on to the weighted normal modifier. I'm going to copy the second example, where the vertex normals were computed simply by averaging the face normals. Now let's go over to the modifiers tab, click add weighted normal. Hopefully right away we will be able to see the change. So now it's set in the weight mode. We can control the fall off by tweaking the weight parameter. If we set it to 100, bigger faces will have more influence or more weight over the look of the shading and over the direction of the vertex normals. So let's apply the modifier and take a look at the actual split normals. So basically, that means now that the vertex normals that exist between the edges of two faces are biased or weighted towards the larger face, instead of being halfway bisection between the angles of those faces. In a nutshell, if the surface is flat, and if it's big enough compared to like small bevels in between and that sort of stuff, it should command all the vertex normals to align with its normal. Awesome, now let's have a closer look at the settings of the modifier. Maybe you'll be able to pick up something interesting. So yeah, as we mentioned, we have the face area mode, which weights the vertex normals according to the face area, and if we put up the weight a little bit higher, it makes the model look like the reference one on the left, which is great in my opinion. The Keep Sharp checkbox enabled just tells the modifier to not mangle the sharp edges, if there are some. Maybe there are interesting ways of utilizing that feature, but honestly, I don't see a whole lot of them. Well, maybe in some exotic cases you may want some edges to be sharp, but yeah. If you stumble across any interesting ways of utilizing this feature, just let us know. Drop us an email or leave a comment. Yet another option found in this drop-down is corner angle. And basically that's how the default smooth shading algorithm of Blender works. Let's prove it. Shift D to duplicate the model. remove the modifier, and yeah, practically it's the same as just not adding any modifiers, especially when the weight is set to 50. And the third option that we have is basically a multiplication of the previous two methods, face area multiplied by corner angle. It almost works like a slider that you can use to switch from the face area to the corner angle. Again, personally, I don't see myself using it very often, but maybe I will find some interesting applications for that feature. Right, yet another option is called phase influence. Basically, it allows you to fine-tune how the faces affect the shading by assigning the additional contrast or additional weights to the faces. You can set face to be either weak, medium, or strong. And for example, if you come across the situation where the multiple faces share the same vertex and their weights were set to weak, medium, and strong, then only the normal associated with the strong face will be used to set the final result. It works pretty well with the new bevel modifier, because now we can control the strength of the newly generated faces, and that's pretty interesting. Look at this. By default it's set to none, but we can set it to new. So the faces generated by the modifier will receive additional strength, or we can set it to affected. So even the faces that touch the geometry generated by the bevel modifier will also be taken into account. This surprising synergy between those two modifiers is pretty exciting. We were talking about it in the bevel tutorial, also one of the tutorials from the hard surface modeling update for Blender 2.80 and beyond. Feel free to watch it. You can find it on YouTube or yeah, whatever. Okay, and the last slider that I wanted to showcase is threshold. Imagine the situation that we put up the weights to 100 and some regions of the mesh start looking pretty weird, because we'd better use some averaging for this particular area. What we can do is use the threshold parameter as a weights rounding threshold. So if two angles differ by less than that threshold, they will get equal weights and thus extra smoothness. But here I disabled weighted normals, and I can't help but mention that hardened normals actually does the same thing as weighted normals. What? But we want to have the full control of the original modifier. Anyway, next, before wrapping it up, let's take a look at some use cases. If you happen to have the bevel modifier in place, you can start off by enabling hardened normals and see if it fixes all your issues, because under the hood it works in a pretty similar manner to the weighted normal modifier. But yeah, nothing can beat the original one. In this example, I found out that we should take the threshold a little bit lower, because some faces were averaged together, and that is not something that is welcome here. But actually, no matter how cool it is, there are cases where a different approach would be more optimal. Who knows, maybe you need that skewed interpolation of lighting across the surface of the mesh. Here, for example, the surface is perfectly flat, but the lamp is supposed to show a little bit of curvature. So after enabling shade smooth and setting the auto smooth angle, and actually it worked right away, but I ended up tweaking it for some reason. So I think it's awesome that it shows some fake curvature. That is much better than sterile, flat, boring surface. That's a lamp. Ultimately, the creative decision of how to treat vertex normals is completely up to you. Different visual styles bring different conventions in terms of how to treat vertex normals and shading. In that sense, Team Fortress is radically different from Alien Isolation or from Star Citizen. That, by the way, these last two games that I mentioned, the creative departments of the studios producing these games used face-weighted normals everywhere as a part of a pipeline. So I hope you enjoyed the new brick in the wall of hard surface awesomeness. My name is Gleb Alexandrov and you're watching the hard surface modeling video course update for Blender 2.80 and above. Thank you for watching.